Hey friends, we need to take a look at Unit 4, Lesson 12 together here. And we're going to work through these problems together, so you should make sure you have some kind of calculator with you. I'm going to show you how you can do all this with your any kind of regular scientific calculator, and I'll also be using my cell phone calculator. So whatever you have, we can use that as we work through these. If you have a graphing calculator, you can certainly use that too. I'll show you briefly how to use that there. Lesson 12 brings up this really important number in math called E. And it's called E because it's named after this guy named Euler. And Euler discovered this number. We'll see how he discovered it in section 12.2. This is a pretty nice lesson to help us first of all review some of our past information and then move us forward. So 12.1 is where we're matching situations and equations. This is kind of a review of lessons 1 through 8-ish, where we're starting to think about how we can write these equations, change the time span, and start putting them into action. So this isn't anything new. This is just some review about how we could take a word problem and match it to an equation. So I see they all start with 400. I see some of them have a rate that is doubling, and some of them have a rate that's cutting in half. Some of them have a rate that's growing by 25%. This one looks like it's losing 25% of its value. So that was a key idea maybe on our quiz about that truck value that you may have missed. This is telling me that it's losing 25% of its value. That means it gets to keep 75%. So this one is growing by 25%. This one's cutting in half. So I might suspect maybe a half-life with this one. So it's just being able to interpret some of these values going on here. Okay, these ones are doubling over here. So a scientist begins an experiment with 400 bacteria in a petri dish. The population doubles, so there's our growth factor, every 10 hours. So we need a function that gives the number of bacteria in T hours. So again, starting with 400, doubling each time, and it doubles in 10 hours. It wants to know every single hour. So I would be looking at something like this. Now I don't have an exact match up top, but I do have these two things that are doubling. And I know I don't want every 10 hours, 10 times t. I want to take 1/10 of t. That's what this is saying. However many hours we have, we're going to divide it by 10. That's the same as multiplying by 1/10. So number 1 is going to match up with our function k of t. Number 2. And feel free to go ahead and hit pause right now and try to work ahead the rest of these to see if you get the same answers once we talk through those solutions. A patient takes 400 milligrams. There's our starting value. The amount of medicine in her bloodstream decreases by 25% every 10 hours. Maybe you're already seeing that that's going to connect up here. If it decreases by 25%, that means we have our starting value of 100%. It decreases by 25%, so we're subtracting. That means it keeps 75% of its value every 10 hours. And if that's the case, we would have a 0.75 multiplier here. It does that every 10 hours. We want to know every 1 hour, t hours, so we'd have to divide however many we have by 10. And we are definitely matching up here with h of t. Again, that 0.1 t is the same as finding 1/10 of t. And so we're going to match this guy with function h. Number 3 is telling us half-life. Maybe you already know what that is then. Which equation? Our half-life of a radioactive element is 10 years. We start with 400 grams of something. It cuts in half every 10 years. So if I want the amount left any t years, it would look like this. 1/10 of t, another way we could write this is 400 times 0.5, just writing half as a decimal, and raising it to the 1/10 of t, 0.1 t. And up top, that is going to match function f. And last but not least, didn't even need a calculator for any of these things. Pretty cool. In a lake, population of a species of fish starts at 400. The population is expected to grow by 25%. That means we're keeping the full 100% and we are adding 25% to it. That's 125%. Turning that to a decimal for a multiplier, we have a 1.25 multiplier. It grows that much in a decade, so my exponent is going to be every 10 years. We want to know every t years. So we have our 400 times 1.25 raised to the t over 10, and that is matching up with our function g. So being able to take some problems in words and turn them into equations so we can apply them. So again, a nice little review here from lessons 1 through 8, but let's see where lesson 12 is taking us as we continue onward. Here is 12.2, and it's a notice and wonder that's happening. So if a spot of mold is found on a basement wall, its area is about 10 square centimeters to start with. So here is that starting point of 10 square centimeters. And this is 3 representations of the same function of a model that shows how it's growing. So we have it in a table, we have it in an equation, and we have it in a graph. And we're thinking just about things that we notice and wonder here, all right? So maybe we see this idea, and maybe the first thing that you're wondering or noticing is that there's this e value here. And we can see that it's growing exponentially, that our values seem to be matching what's in the table. And if I were to look at what that multiplier is starting from 10, and what would I have to multiply it by to get my first week? Well, if we have 10 times something multiplier to get us to 2.7, or I'm sorry, 27. I'm already starting to think of how I'm going to do this. Divide both sides by 10, and we'd find that that growth factor, that multiplier, is about 2.7. And I just want to check it again to see if it's the same from our 27 to 74. So I'm going to use my calculator for this, clear that out. And I'm thinking, what is 74 divided by 27? And I find that multiplier is something a little bit more specific, a little more decimals going on here, 2.74. So it has me wondering about the rest of these multipliers. From here to here, it's a 2.716. Oops. Got to take the 546 and divide it by 201 to see what the multiplier is. So I finally got 2 of them that are exactly the same, the 2.716. If I know that this multiplier here, as we went from one to the next, by doing division, it seemed like it was getting close to this 2.716. It started as 2.7, then 2.74, 2.716, and I got that a couple times. Because that's my growth factor going on here, I think maybe this e value that I haven't ever seen before might be some kind of growth factor that's close to 2.716. It still has the same starting, there's our growth factor, the E, and then raising it to the time in weeks that we're giving it. So because we know we're looking for a single growth factor instead of these different ones that slightly change in our table, that might be because of rounding going on. We can actually figure out what this E value is. So when we think about what do we notice and wonder, we've definitely had a couple noticings and wonderings up there. But I want to really focus in on this E value. E is a set value. It doesn't change. E is a number that was founded by this guy, this mathematician called Euler. And Euler found this idea that if he watched things grow in population, if he watched what we call continuous growth, it's happening again and again. So this bacteria doesn't just like get to 27 square centimeters and then stop for the week. It is continuously growing. It's growing every single second, every single moment, every single chance that it has to change. It is making these teeny tiny changes in these itty-bitty time spans, and we can use E to represent that. E is very much like pi that has a set value. Pi is equivalent close to 3.14159. E is a button on our calculator. It's also on our cell phones. So I'm going to go to my cell phone calculator. Let me just turn on my password there. And so we're going to be using, I'm trying to use some of the tools you might have at home. And you probably have a cell phone calculator or one on your Chromebook. If you turn it sideways, we see we have a lot more possibilities. And we have seen some log values and how we can use those to type them in on our calculators that we have. But we want to look at what this E thing is. And I see my E is right here. It's not this double E capital, it's this lowercase e. And when I just hit E, I see what that number is equivalent to. E is really close to 2.71828. And then it goes for like 1828, for a while, but then it has a 4590459. It's got this weird repeating pattern, but it is changing in chunks like that. So E is this number that we're going to start using. We're going to use E for anything that is called continuous growth. Or something that is growing continuously. And we're going to see that they use it for everything from populations of bacteria and mold, like we're seeing up here, to populations of animals and species, but also to things like money, right? When you invest money into the bank, they don't just wait until like the end of the month and then calculate your, like the percent that you get back. They do it every single second. Banks get more money that way if they get money continuously growing from their investments. And so we're going to see continuous growth is very much used for things like population. Definitely for things like money, investments. And we're going to see that it's very much used in science to see some values that are changing, like bacteria and viruses. All right. 12.3 is really not that helpful. What it's just reinforcing is that we're going to start seeing some equations like this that are equivalent to each other. We'll deal with that in a future lesson. But knowing that E is approximately equal to 3.718, and that it is going to somehow be connected when we have a teeny tiny rate that is raised to a great big giant number. If you're really curious about this, graph these two in a Desmos screen and see what they look like, because they should be incredibly similar to some ideas, and how when we put in some very small x values for each, we may see not much of a difference, but as x gets bigger and bigger and bigger, we're going to see a little more separation going on with those two. That's really our whole idea. So you can see our lesson 12 summary is very, very short, that e is approximately 2.78. Just like pi is a set number that's irrational, e is also a set number that is irrational. And there's his name, Euler. We call it Euler's number. We're going to use this in future lessons. In fact, it's so useful that there is a whole other button on your calculator that uses e. If you are using a calculator like this, you might see it above. So here is e, its second ln button. We're going to see what that ln is in a future lesson, but here's that same number. E to the first power is 2.718281828. Thanks, friends.